Welcome back to the podcast, Yuvs. We're diving deeper into Chapter 7 of Python for algorithmic trading, focusing on real-time data and sockets. This chapter really emphasizes the importance of sockets for algorithmic trading, right?
Absolutely, Matthew. It's crucial because, unlike backtesting, where data is readily available, real-time market data arrives constantly and in large volumes. You need a system to handle that influx. Sockets provide the efficient connection and communication.
So, you're saying sockets are like the highways for this data?
Exactly. Think of a socket as a specific endpoint on a network connection. A socket address, combining an IP address and a port number, identifies a particular location for communication. The socket protocol, like TCP, defines the rules for how data travels. And a socket pair is essentially the connection between two endpoints, like two computers exchanging information. The Socket API gives programmers a way to interact with and manage these connections programmatically.
And you're highlighting 0MQ as a key tool here. What makes it special for this type of real-time trading application?
0MQ is a lightweight, fast, and scalable socket library. It's incredibly important for high-frequency trading situations because speed and reliability are critical. It supports various communication patterns, and the publisher-subscriber (PUBSUB) model is particularly relevant. You have one publisher sending data and multiple subscribers receiving it, like a radio station broadcasting to many listeners. This is ideal for disseminating real-time financial data, like tick data, to numerous algorithmic trading systems simultaneously.
So, if I understand correctly, a trading platform or exchange acts as the publisher, and my trading algorithm is a subscriber receiving the tick data?
Precisely. The chapter describes a scenario where you have a tick data server that publishes this live price information, and your client program, connected to this server, is designed to subscribe to receive and process it. This real-time access to constantly updating data is critical for executing trading strategies.
You mentioned tick data. What exactly is that?
Tick data represents the smallest unit of price change. It's basically the up-to-the-minute updates on market prices. Imagine tracking changes in the euro to US dollar exchange rate. Each change is a tick. So your program would be receiving these real-time ticks to enable real-time trading strategies.
And the example code you mentioned, it's crucial that you run these parts of the application in different terminal windows or Jupyter kernels. Why is that?
Yes, because the server application and the client application need to run concurrently. The publisher server needs to be constantly sending data while the subscriber, client, is receiving and processing it. Running them in separate processes ensures smooth, real-time data flow, which is critical in a high-volume trading environment. Trying to do it all within a single Jupyter notebook will often lead to problems.
Excellent. So the example structure, using the server in one process and the data retrieval in another, is a core component of real-time trading systems.
Exactly.
Welcome back to the show, Eve. We're diving deeper into this Python for algorithmic trading book today. We're looking at a simple tick data server, and it's using 0MQ, right?
Yeah, absolutely. It's a great way to get started with real-time data, and 0MQ is a powerful message queuing library. It's super efficient for low-latency applications.
Okay, so the server is simulating instrument prices. Can you walk us through how that simulation works? Specifically, what's this geometric Brownian motion thing?
Sure, it's a common model for simulating stock prices. It assumes that price changes are random and related to the current price and some other factors. And essentially, the change in price is proportional to the current price, and it incorporates volatility and a risk-free rate of return.
So, the formula equation 7-to-1, that's the key to the simulation? Can you break that down for us?
Absolutely. The formula basically gives us an approximate way to update the stock price over small time intervals. It takes into account the current price, the risk-free rate, the volatility, and a random component that's crucial for capturing the stochastic nature of market movements. The key part is that it's a standard normal random variable. Essentially, it generates the random fluctuations in the price.
So, the code uses an Euler discretization? Can you explain that in plain terms?
Right. Instead of trying to solve the continuous geometric Brownian motion equation, which is very complicated, the Euler method gives us a simple way to approximate the price changes at discrete time intervals. It's like taking a series of tiny steps to approximate the overall trajectory.
And the instrument price class? How does that fit into the overall simulation?
Well, this class encapsulates all the parameters needed for the price simulation. It stores the instrument symbol, the current price, the volatility, and the risk-free rate. The crucial method is simulate_value. This method calculates the new price based on the previously calculated price and a randomly generated z-value that reflects the market's unpredictable movement.
You mentioned randomizing the time interval between price updates. Why is that important for real-world tick data?
It's crucial because real-world market data doesn't arrive at evenly spaced intervals. Prices change at different rates depending on various factors. By randomizing the arrival times, we're creating a more realistic representation. It's a significant difference from, say, closing prices that might come at the end of a trading day, which are often used in Monte Carlo simulations.
The time.sleep, random.random, *2 line. That's where the randomization happens?
Precisely. It pauses the execution for a random amount of time between 0 and 2 seconds, mimicking the random fluctuations in market data arrival times. So it's essential for representing real-world market characteristics.
And the code sends the simulated price data via 0MQ. What about error handling? Does this code account for potential errors?
Well, that's important. For robustness, this code usually wouldn't handle error conditions very gracefully. You would need to add checks or other techniques to account for situations such as network issues. In the real world, you often have more sophisticated error handling, like monitoring the socket for errors, implementing retry mechanisms, or logging.
Great insights. We've learned how the simulation works, how it represents real-world market arrival times, and why this is important. Thanks, Eve.
You're welcome, Matthew. It was great discussing this topic.
Welcome back to the show, Eve. We're diving deeper into Python for algorithmic trading, specifically looking at how to connect a simple tick data client. So, the code snippet we're looking at is for a client, right? Can you give us a high-level overview of what this client does?
Sure, Matthew. This client, essentially acts as a receiver for tick data. It connects to a server that's publishing that data. Think of it like a subscriber, constantly listening for updates.
Okay, so it's a reactive system. And you're mentioning a server is publishing data. Can you elaborate on the role of the server in this architecture?
Absolutely. The server is responsible for generating and sending the tick data, the price updates, symbol information, all that. This client, the part we're looking at now, just focuses on receiving and displaying it. They're separate processes, essentially.
Right, a classic client-server model. The code starts by importing the 0MQ library. Why is 0MQ important here?
0MQ is a high-performance messaging library. It's optimized for fast data exchange, which is crucial for real-time trading applications, and avoids using the operating system sockets directly. It provides a robust messaging queue that's very efficient.
Okay, interesting. It's not just some regular socket. It has this 0MQ architecture. And the client code then creates a 0MQ context and a subscriber socket. Can you unpack these parts?
Yeah, the context is like a container for all 0MQ resources. Think of it as managing the connections and resources, like opening and closing sockets, automatically. Then the subscriber socket is specifically designed to receive messages, and it's set up to subscribe to a specific channel. Importantly, the code specifies the channel symbol.
So it only receives updates for a given symbol?
Well, not strictly. The socket subscribes to a channel. While this example has one channel, real-world applications often use a socket connection to receive data from many different symbols, which is crucial for handling multiple assets in the portfolio. Imagine a portfolio with 10 stocks, all needing tick data. It's more efficient to have a single connection, and then subscribe to channels for each.
Got it. So, the code connects to the server using a TCP address, right? Does the port have any significance?
Exactly. The TCP address and port combination defines the location of the data server. The server has to be running on that port and listening for the connections to that address.
That's a crucial connection point.
And the rec_string function, in the while loop, retrieves data in a string format. Why not receive it in a different format like JSON? Is it just a matter of preference, or are there other considerations?
Not entirely preference. The data sent from the server is string-based in this example, as it makes the client code simpler. But string-based communication is often used alongside standard formats like JSON, in combination, in real applications. It depends entirely on how the data is structured, what data is received, and how it is to be processed. It's a very common practice to use string-based for basic data retrieval, then converting to something more structured like JSON or a dedicated object format for further analysis and processing, like generating trading signals, or doing real-time data visualization. Sending Python objects directly via send_pyobj and rec_pyobj is also possible, but generally serialization and deserialization with Pickle is common, but for languages other than Python, it's more useful to use standards like JSON.
So, we've learned about the client-server architecture, important aspects of 0MQ in this context, and also why string-based communication is often preferred. Thanks for breaking this down, Eve. Welcome back to the podcast, Eve. We're diving deeper into real-time signal generation for algorithmic trading, specifically how it works with online algorithms. We were discussing how these algorithms only use current and previous data, unlike offline algorithms that have a complete dataset. Can you elaborate a bit more on the practical implications of this constraint?
Sure, Matthew. The key takeaway is that online algorithms have to be incredibly responsive and adapt quickly to changing market conditions. They don't have the luxury of looking at the entire history of the market to make a decision. They have to make a decision in real time based on what they know at that moment. This is crucial for financial trading, where you can't afford delays, and potentially large losses can occur.
Right. So this real-time constraint forces a focus on incremental updates and efficient data processing. How does this online algorithm handle the data flow in practice?
Well, it's a continuous process, collecting tick data and processing it as it comes in. The example script shows a pandas data frame df used to store this incoming tick data. Crucially, each new tick, represented as a symbol and a value, gets appended to this data frame immediately.
Okay, that's clear. And the timing is important too, so it knows when each tick arrives.
Exactly. Timestamps are generated to track when each data point is received. This time information is fundamental for calculating things like momentum over time intervals, like those 5-second intervals in this example.
So, after accumulating the tick data, how does the algorithm calculate the momentum?
The key step is resampling. The df.resample, 5s, label equals right last, line takes the tick data and groups it into 5-second intervals. The label equals right ensures that the timestamp for each resampled data point is at the end of the 5-second interval. Then it takes the last data point from each interval, which is crucial because that is the most recent data available.
So, it's selecting the last data point from each 5-second interval, then calculating the momentum? That's crucial.
Absolutely. Then the code calculates log returns using dr returns equals np.log, dr/dr_shift1. This shows the percentage change between consecutive 5-second intervals, which is a key indicator of price movement. Following that, it calculates the average log return over a window of 3 resampled data points using dr momentum equals np sign, dr returns rolling mom mean. The sign of this rolling average momentum over the window dictates whether to take a long or short position.
That's helpful. And this rolling calculation, is it critical in this context?
Absolutely. The rolling function is crucial because it captures the trend over time. The algorithm uses the rolling mean to smooth out short-term fluctuations and look for larger patterns. A rolling calculation is fundamentally important for filtering out random noise in the data.
And finally, how are signals generated based on this momentum?
The code checks if the second-to-last momentum value, this is crucial because the last value is incomplete, is 1.0 or -1.0, triggering a long or short market position, respectively. The output example shows exactly how the algorithm displays the new signal and the accompanying position.
So, the script is essentially accumulating data, resampling it, calculating returns, determining the momentum, and then based on the momentum sign, it generates a signal and takes action. Is there a minimum amount of data required before any trading signal is generated?
Yes, the min_length variable controls this. The algorithm needs enough data points to have a reliable momentum calculation before generating a signal.
Very interesting, Eve. Thank you for clarifying all of that.
You're welcome, Matthew. It's important to note that this is a simplified example, real-world algorithmic trading systems would incorporate much more complex strategies and risk management. It's a good exercise, though, to implement SMA and mean reversion strategies as online algorithms to gain a better understanding of the concepts.
Hey Yves, welcome back to the show. We were just discussing the power of visualizing data, and now we're diving into real-time streaming data. Plotly seems like a great tool for this. Can you give us a quick rundown on why it's so effective?
Absolutely, Matthew. Visualizing streaming data in real time can be a real challenge, because you're dealing with constantly updating information. Plotly, though, makes it pretty straightforward. It's a powerful tool for creating interactive plots, both static and dynamic. You can essentially watch data flow live and see how it evolves over time.
Okay, so it's more than just a static graph. It's interactive. What makes it particularly useful for streaming data, exactly?
Well, it's interactive in the sense that you can zoom, pan, and explore the data in different ways. That's crucial for real-time insights. You're not just looking at a snapshot, you're watching the data unfold. You can track trends, anomalies, and potentially react in real time to them. You can also apply filters, change the visualization type quickly, things like that.
Right, makes sense. And you mentioned installation. What packages do we need to install with Plotly for this real-time visualization, especially if we're using JupyterLab?
Yep, absolutely. To use Plotly effectively in JupyterLab, you need to install a few additional packages. The core Plotly package, of course, conda install Plotly, is essential. And then there are JupyterLab extensions.
So, JupyterLab extension install commands, are those a separate set of installations needed for Plotly specifically, or part of JupyterLab setup in general?
They are extensions for JupyterLab. You need to install the JupyterLab Plotly extension. So you need JupyterLab extension install JupyterLab Plotly. This makes sure Plotly integration works smoothly within the JupyterLab environment. Also, you need the @Jupyter widget/JupyterLab Manager to manage the extensions and Plotly widget to support Plotly's interactive components within JupyterLab.
Got it. So we're installing Plotly the package, then JupyterLab extensions that add Plotly to our Jupyter environment, and the widgets for interactivity.
Exactly. These additions handle the specific interaction of the Plotly visualizations within the JupyterLab interface. All these installations ensure that when you create Plotly charts within Jupyter Notebook, you can interact with them smoothly, just as you would with a standalone Plotly application.
Excellent, Yves. That clears up the installation process. Now, if we're looking to actually implement this, what are the first steps for actually creating those interactive charts?
Well, the first step is to import the necessary libraries, creating your Plotly figure and updating it using Plotly's Plotly graph_objects or Plotly Express to reflect the streaming data in real time.
Welcome back to the show, Yves. We're diving deeper into Python for algorithmic trading, specifically how to stream data and visualize it. Let's talk about this chunk. We're looking at plotting real-time stock data. So, we've got the Plotly figure widget set up. Can you walk us through how the socket connection works to get the live tick data?
Sure, Matthew. This is a critical part. We're using ZeroMQ, a high-performance message queuing system, to handle the communication between our Python script and the data source. Essentially, the data server is sending messages over the network, and our script is listening for them.
Okay, so this ZMQ.SUB socket, what's the purpose of that? Can you unpack socket.connect, TCP, //0.0.0.0:5555?
The ZMQ.SUB socket specifically subscribes to a topic. It's a pull-based system. The data server is pushing messages to this socket. Socket.connect, TCP, //0.0.0.0:5555 establishes a connection with a server running on port 5555 on your local machine, crucial for real-time communication. The TCP, // part designates a TCP connection. ZeroMQ handles the low-level details of efficient network communication.
So, the server needs to be running in parallel? And how about socket.setSockOpt_string, ZNQ.subscribe symbol? What's that doing?
Yes, absolutely. A separate process on the same machine runs the data server, and it delivers real-time tick data. Socket.setSockOpt_string, ZMQ.subscribe symbol is vital for filtering the data. It tells the socket to only receive messages tagged with the symbol string, meaning you only get data for the particular stock symbol in this case. Without this, you'd get any data the server sends. It's crucial for efficient data handling.
Right, so we're getting the real-time prices. Then we're splitting the message to extract the price. Why are the times and prices stored in lists?
Because the data arrive.
Got it. Then, finally, you update the figure data 0.x and figure data 0.y with the times and prices list to plot the data on the go. Elegant. Is there a practical limit to how many points can be plotted? And is there a way to manage potential data loss or lag?
You're spot on, Matthew. Yes, there's a limit based on the plot's capacity to handle updates. You might want to consider techniques like circular buffers or removing older data to maintain a consistent data stream and plot without overloading the plot. Handling potential delays or data loss will require strategies for error handling within the 0MQ communication or the plotting section. A potential strategy would be adding error handling or a timeout when waiting for data.
Welcome back to the show, yous. We were just talking about real-time streaming plots in Python, and now we're diving into how to visualize multiple data streams simultaneously. This chunk introduces the concept of adding, multiple moving averages, not just the raw price data. Can you unpack this for us, please?
Absolutely, Matthew. We're building on the previous example of visualizing price ticks in real time. Now, instead of just one line for the price, we want to show, say, a 5-day simple moving average, SMA, and a 10-day SMA alongside it. This lets us see trends and potential trading opportunities more clearly, right?
Right, that makes a lot of sense. So, the code creates a figure widget, which is a way to display interactive plots in a Jupyter notebook, correct?
Exactly. It's using Plotly's figure widget, which is great for dynamic updates. The crucial part is creating 3 separate scatter plots within this figure. One for the price itself, one for the 5-day SMA, and another for the 10-day SMA. Notice the line attributes, which give each SMA a distinct style, like dotted and dashed lines, making them easier to distinguish visually.
Okay, so we're adding aesthetic elements to make the plots readable. The code then gathers the tick data from a simulated server. How does that work?
The code snippet is using a placeholder for a real-world socket communication. It reads the incoming tick data, symbol and price, from the server, effectively. And then it stores these in a pandas data frame.
Got it. The key part is calculating the SMAs after each update. How is that done?
Yeah, and that's where the rolling function in pandas comes in. It calculates the moving average over a specific window. For example, df sim rolling 5 mean calculates a 5-day SMA for the current symbol's price. And a new 10-day SMA in df sim rolling 10 mean is calculated. Crucially, this is done after each new tick comes in, so the averages are constantly updating.
So, it's a continuously updating calculation, rather than a pre-calculated value?
That's right. The calculated SMAs are then stored as separate columns in the data frame. And then, these values are used to update the y-axis values for the corresponding scatterplots in the Plotly figure widget.
Okay, I follow that. This is a very dynamic way to present the data. And what about the x-axis? It's updated too, right?
Exactly, Matthew. The figure data, ix equals df index part ensures the x-axis values align with the corresponding timestamps in the data frame. Because the data comes with timestamps, this is super important. This way, we see the moving averages plotted against the correct time points.
Interesting. You mentioned that this type of plot is useful for online trading algorithms. Why is that?
Well, tick data is often too granular for these kinds of algorithms. So, resampling is often necessary.
Thanks for that clarification. That's really helpful to understand the broader context. So, integrating a real-time trading algorithm based on these SMAs would involve the step of resampling.
Absolutely. A trading algorithm built on this type of data would analyze the relationship between the price and the moving averages to detect possible trends and make informed trading decisions.
Great. This really helps solidify the idea of combining streaming data visualization with sophisticated trading algorithms. Thanks again, Yves.
My pleasure, Matthew.
Welcome back to the podcast, Yves. We're diving deeper into Python for algorithmic trading, and today we're looking at creating dynamic real-time visualizations. You've mentioned creating multiple subplots in Plotly streaming plots. Can you elaborate on that, particularly how those subplots are set up and what they're showing?
Sure, Matthew. We're building out a more comprehensive view, essentially creating a dashboard. We're looking at three key elements: the price data, the log returns, and the momentum calculated from those log returns, all in real time. The key here is that Plotly's figure widgets let us update these plots dynamically as new data comes in. Each subplot provides a specific piece of the information picture.
So, you're building, a sort of visual representation of different trading metrics?
Exactly. The first subplot shows the actual price of a particular symbol over time. The second subplot focuses on the log returns, which essentially measures the percentage change in price over time. Crucially, these log returns are fundamental to understanding the volatility and potential growth of the asset. It helps to smooth out the data and give a better representation of the trends. The third subplot then shows the momentum indicator. That's calculated by taking the rolling mean of the log returns over a set period, often 10 in this case. This gives a sense of whether the asset's price is trending upward or downward.
Okay, so the code seems to be using make_subplots to create the figure layout. Can you unpack the key aspects of how it structures the three different plots and connects them together?
Right. We're defining rows and calls of 3 and 1, respectively, in make_subplots. That tells Plotly to arrange the subplots vertically, in a single column. Then shared_axis equals true is crucial. This ensures all the subplots share the same x-axis. This is essential because we're charting the different metrics over the same time period. This gives us a unified timeline for comparing the various metrics.
Got it. So the plots are aligned on the timeline, showing the same time frames for each metric. How are the actual traces, the lines, points, etc., added to each subplot?
Ah yes. We're using append_trace with specific traces in Go. Scatter to add the data to each subplot. The parameters like row and call specify where the trace should go in our 3x1 grid.
That's excellent. So, the process seems straightforward. Create the figure, add the traces, and update the data dynamically as new information arrives. How is this data update implemented?
Yes, the example shows it in a loop. New data is read from the socket, and then it's inserted into a pandas data frame. The code then updates the X and Y data of each trace using the updated data frame, effectively replacing old data with the live data. Finally, the figure show command displays the plots. The figure data part is crucial in this process, as it allows direct manipulation of the traces within the figure.
Welcome back to the podcast, Yves.
Absolutely, Matthew. Streaming data isn't always best suited for a time series plot, especially when the focus is on the magnitude of the data point at a particular moment. Bar charts really shine in these situations, allowing you to quickly see changes in the values over time.
Right. So this sample data server for bar plot script is serving up data formatted for a bar chart. Can you break down what a typical data message looks like?
Sure. Each message contains 8 floating point numbers. Imagine them as representing different aspects of a trading strategy, or maybe sensor readings from a physical process. Crucially, the x-axis data doesn't change. This means we're plotting values against a constant set of categories, which is ideal for comparing them.
Got it. So the x-axis is fixed like a B, C, D, F, G, and H. Why is that helpful in this context?
Precisely. This lets us focus on how the values associated with each category are changing over time. The code then effectively reads these messages in a loop and updates the height of the bars accordingly. Imagine tracking the price of multiple assets.
Okay, that makes sense. The code's fetching these messages, right? What's the important part in terms of how the socket's being used to retrieve that data?
Yes, it's connecting to a 0MQ socket. The socket is set up to subscribe to messages coming from a server that's running the data. The crucial part is the socket.rec_string call. It receives the message as a string, and then that string is processed to extract the numerical data. Importantly, the socket.setSocket_string, ZMQ to subscribe, line is critical. It's the subscribe command to the socket.
Makes perfect sense. So, once it's received, it's parsing the data from the string. What's the procedure for transforming the string into a usable numerical format?
The message string is split using the message split method, likely separating the numerical values by spaces. Then it uses a list comprehension float, n for n in y, to convert each of these string values to their floating point equivalents. This is a common Python idiom for converting a collection of strings to numeric types.
Okay, so it's taking a string, splitting it, converting each piece into a number, and then assigning it to the y values for the bar chart, based on the fixed to through h categories?
Exactly. That's how the bars get their height updates. The height of each bar reflects the numeric values associated with its corresponding category. And finally, we're updating a Plotly Go to Figure widget, which is Plotly's interactive charting library, and it's displaying these changes dynamically, giving us a live visualization of the data.
That's a really clear breakdown, Yves. It's crucial to understand this pipeline to leverage streaming data effectively. This gives a good practical example of how to take data from a streaming source and plot it on a bar chart. Thanks for walking us through this.
You're welcome, Matthew. Glad to help.
Welcome back to the podcast, Yves. We're diving deeper into Python for algorithmic trading, and in this segment, we're looking at real-time data handling, right?
Yeah, absolutely, Matthew. We've been discussing historical data, backtesting, and now we're moving into the dynamic world of live streaming data. This is crucial for real-time trading strategies, where you need to react immediately to market changes.
Precisely. The chunk highlights tick data as the most important streaming type. Can you elaborate on why tick data is so critical for algorithmic trading?
Tick data represents the smallest price changes of a financial instrument. It's essentially a record of every price update, including the time and the price itself. So, for real-time trading strategies, having the instantaneous updates on price movements is paramount. You need to know exactly what's happening in the market to react accordingly. For example, if a stock suddenly drops, your algorithm needs to know right away to potentially execute a sell order or adjust its trading strategy to account for the sudden change.
So, sockets are your tool of choice here? Can you explain why?
Sockets are essential for handling real-time data streams. They establish a continuous connection between your trading application and the data source. This allows for a continuous flow of data, as opposed to polling for updates. Polling can lead to significant latency, which in real-time trading is often detrimental. Real-time data is best received using a continuous stream over sockets, ensuring minimal latency and responsiveness.
You mentioned a library called ZeroMQ. What makes it a good choice for this?
ZeroMQ or ZMQ is a high-performance message queue library. It's efficient for dealing with the continuous flow of streaming data, providing low latency and reliability, which is crucial in high-frequency trading scenarios. And importantly, it's easy to use for creating the server and clients needed for real-time data exchange.
And you're using it to create a simple tick data server that continuously emits sample tick data. Can you explain the concept?
Yeah, that server continuously generates simulated tick data. Think of it as a simulated market feed. This helps developers test and refine their trading algorithms in a controlled environment without needing access to real market data, which can be quite complex or expensive to access. This example server will publish simulated market data for any clients connected to it.
Okay, I understand the server aspect. How do the clients interact with this data for generating trading signals?
The client applications connect to the server using ZeroMQ. They receive the tick data in real time and then use online algorithms to process it. Based on these algorithms, trading signals are generated, like buy or sell signals, for example. It's fundamental to any real-time trading strategy.
And visualizing that data is key, right? How does Plotly play into this?
Absolutely. Plotly is incredibly useful for visualizing streaming tick data within a Jupyter notebook. You can track the real-time price movements with dynamic plots. This allows for real-time analysis and monitoring of the data as it streams in. You can see, for example, multiple price streams in separate subplots for different instruments, or potentially even have all of the price streams within a single plot. This real-time visualization helps you quickly spot patterns, trends, and anomalies in the data, leading to better decision-making in a trading environment.
So, in summary, we've covered historical data, real-time streaming data, and the importance of visualization. It all seems like a pretty crucial step towards building a robust algorithmic trading operation.
Precisely. This capability allows you to integrate and handle both historical data and real-time data, which is crucial for any algorithmic trading system. You need to be able to learn from the past and react to the present.